To start off, you'd like to draw a free body diagram of the problem. That's the radius. There's the object that's spinning. And it weighs 2.5 kilograms. And this is 0.5 centimeters long. We know the relaxed spring is 0.4 meters. The mass, like I already said, is 2.5 kilograms. And the new length, or the stretch length, is 0.5 meters. The way you work this problem Sorry, I had a malfunction. But we know also that it has 25 revolutions. That happens over a time period of 10 seconds. Well, we're going to use the formula of mv squared over r equals F net, or in our case, Ks, the stiffness. The only problem is, right now, we don't know V. So, in order to find V, we have to solve V equals 2 pi times how far it is from the center, which ours would be 0.5, times how many times it's rotated, divided by the amount of time it took, which is going to equal 7.85 meters per second. Oh, shoot, sorry. With that, now we go back to our formula. mv squared over r equals Ks. We know our mass, which is 0.4, times our speed, which we recently found, 7.85 squared, all over the radius, which would be 0.5, which will equal 308.1 newtons. And we know it's a newton because 1 newton equals kilograms times meter per second squared. Next, it wants to know all the objects that are exerting a force on the ball, which will be, I said gravity, but it's not an object. So that's also equal to Earth. Also have the string and the spring. For the free body diagram, we have the ball. We have a spring exerting a force pulling the ball. We have the string pulling away from the ball. And we have gravity for the Earth, gravity pulling down. The magnitude of the forces took me a little while, but I finally figured it out. It's the sum of f of x is going to equal 0. The sum of f of y is going to equal 0. From a free body diagram, we know that it's at equilibrium because it's not moving. So that's going to stick us with, for our x's, from ft, which is the tension on the string, which we're looking for, minus f s of x. It's going to equal 0 also. And then f s of y minus f w, which Fw is our weight, which is mass times gravity. Alright, so we have Fs of w, Fs of y equals Fs cosine theta, which equals k delta x cosine theta. And Fs of x equals Fs sine theta. From this we can take and make, for Fs of y, we can do mass times gravity equals k, which is what we're looking for, delta s, the change in the stretch, times cosine theta, which is going to equal 4.7, that'd be the mass times the gravity, equal to k, what we're looking for, times 4, times cosine 28 degrees, for the angle that was given. Multiply these two, it's going to give you 4.7 equals k times sorry, I went blank. You're going to divide k over, and then you're going to divide this by this. So we're actually going to erase this. Hold on. Alright. I'm going to divide this by 4.7. And we're going to bring k over here. Which then we're going to get k equals 1.33. Now we're going to go back to, now we have to solve for Ft, which would be the tension on the string, which would be Ft equals, we know f of x, Ft is equal to f of x, as given right here, and then f of x is going to be equal to f of s sine theta, which is given right here, which equals K delta, change in the stretch, sine theta. And then we plug in what we know, which would be 1.33 times 4, the difference in the stretch, times sine is going to be 90 degrees plus 28, which is going to equal our FT, which is 4.697 newtons.